Hello and welcome back. In 6.1 we look at the area between curves. So I'll start us with just an XY plane, and we'll have a pair of curves F and G, and we'll assume that they're continuous on some open interval AB. In 6.1 we're going to be looking at how big the area is just between a top curve and a bottom curve. Now, one nice property that these things have, if we add the same constant to both f and g, or subtract the same constant from both f and g, that's really just equivalent to sliding up or down on the y-axis. So the amount of area between f and g would be the same whether they were above the axis or below the x-axis. If this had been our x-axis instead of the original one, the same amount of space would be between curves f and g. So it doesn't matter if we're above or below the axis for this. It just matters which one is the top function, which one is the bottom function. And just as a heads up, occasionally we will have a switch in behavior. Sometimes, let's say this is our function f, and here is function g. We could have a change in behavior on AB. In that case, we just have to set up two separate little mini problems, one where f is the top function and the other one where g is the top function, and we would just add those results together. So how we do this is just through integrals like we did before. So for example, if I want to find the area between y is x squared minus 4 and the x-axis, in other words, y equals 0. We'll do a few places. We'll do on 1, 2. So this is for the x values. X is on 1, 2. We'll try out on -2 to 2. And we'll try out on 0, 4. Now for each one of these, I'm going to make just a quick rough sketch to get an idea where my top function is, where my bottom function is. So for number 1, looking at just the closed interval 1, 2. So plugging in 1 here, 1 squared is 1, 1 minus 4, we're at -3. And 2 squared is 4, 4 minus 4 is 0. So there is part of our curve. As you know, we have a vertex at 0, -4, and we're opening up since this is a parabola. Now the other function that we looked at was y equals 0, the x-axis. Also at the moment, we're just looking on 1, 2. So on this interval, y equals 0 is the top function, and the curve y equals x squared minus 4 is the bottom function. So I would do the integral from 1 to 2 of always top function minus bottom function. Close it up, multiply by dx. So this would give me the integral from 1 to 2 of opposite of x squared plus 4, quantity times dx. So negative 1/3 x cubed plus 4x. So we're just doing the antiderivatives one piece at a time. And then we evaluate from x is 1 to x is 2. So if you'll recall, that just means plugging in the 2 minus what happens when you plug in the 1. So plugging in the 2 cubed is 8, 8 by negative 1/3, negative 8/3. 2 by 4 is 8, which is 24/3. 1 cubed is 1, 1 times negative 1/3 is negative 1/3, and 4 by 1 is 4, which is 12/3. So we have, looks like 16/3 minus 11/3, which would be an area of 5/3 square units. 1 2/3 square units. So that's how large an area is boxed off by those two graphs. So from -2 to same two equations, obviously we're going to have a bigger quantity since we have all of that plus everything all the way back here to this other intercept. So I'm going to give myself a little more room to work here. So there's our curve, there's our line. So we're looking for this area. So on this one, our top function is still the 0. So integral from -2 to 2. Top function 0 minus bottom function x squared minus 4. Top minus bottom. So integral from -2 to 2 of opposite of x squared plus 4 quantity times dx. So we've already seen that that's negative 1/3 x cubed plus 4x. Only now we're evaluating from -2 to +2. So plugging in the +2, we have negative 8/3 plus 8 is 24/3. -2 quantity cubed is -8. Negative by negative kicks us over to a positive. And 4 by -2, -8, or -24/3. So then this is our 16/3 minus a -16/3. So 32/3 square units. Or 10 2/3 square units. So again, more area than the previous problem. Should make sense though. That's included all of the area that we had before plus some extra. Now our third one, our graph is going to look a little bit different. So we're still starting at 0, -4. We still have a parabola opening up. Only now, here at 2 is where our y equals x squared minus 4 and our y equals 0 meet. But we're going all the way to 4. So now, from 0 to 4, I need to really get two sections in order. So I have two different pieces that I need to find. So that's going to be two different integrals. So my first integral is from 0 to 2, and my top function there is 0. My bottom function was the x squared minus 4. Multiply that by dx, and then we're going to add the blue area. So that one, our x's go from 2 to 4. This time our top function is now the x squared minus 4. our bottom function is the 0. And as usual, multiply by dx. So this is the one where folks tend to get tripped up, is when we have sort of a change in behavior as to who's the top function, who is the bottom function. So this one, integral from 0 to 2 of opposite of x squared plus 4 quantity times dx, plus integral from 2 to 4 of x squared minus 4 quantity times dx. Go ahead and pause it and see if you can finish it from there and get see if you can get an area out of this. Okay, welcome back. So we have negative 1/3 x cubed plus 4x, evaluated from x is 0 to x is 2, plus positive 1/3 x cubed minus 4x, being evaluated from x is 2 to x is 4. So I'm going to have a pair of subtraction problems. So plugging the 2 into here, we've got negative 8/3 plus 8 is 24/3, minus plugging the 0 in there, I get a couple of zeros. 0 cubed and 0 times 4. So those are from my red area. These red brackets aren't mathematically necessary. I'm just sort of emphasizing that that's where this chunk is coming from. Our second subtraction problem is coming from the blue piece. So then we have 4 cubed 64/3 minus 16 is 48/3, and then plug the 2 in there. So 8/3, and then we have minus 24/3. So this part is from the blue piece. So we plug and chug on that one, and we'll plug and chug and we come up with an even 16. So 16 square units on the money. Exactly 16 square units, the red area plus the blue area. Okay, so we have you all try one out. I'm going to have you try one of your author's problems. So let's do the area between f of x is x squared minus 9, and the x-axis, in other words, y equals 0. So they won't always specifically say y equals 0. They're going to assume that you know. Y equals 0 if we're talking about the x-axis. So let's try it on 0, 2. And again, this is one of your author's problems. And then we'll repeat on 2, 4. So go ahead and pause it, give those a spin, see what you come up with. Okay, so it should be similar to what you saw before. So x squared minus 9, parabola, vertex at 0, negative 9, opening up. No super surprises there. 0 and 2. 2 squared is 4. 4 minus 9, negative 5. We're still down here. So this is the slice we're looking at here, which means that in this case, 0 is our top function, x squared minus 9 is our bottom function. So we take the integral from 0 to 2 of top function 0 minus bottom function x squared minus 9 times dx. So integral from 0 to 2, do a little cleanup, minus x squared plus 9 quantity times dx. So negative 1/3 x cubed plus 9x quantity evaluated from x is 0 to x is 2. So plugging in the 2, we have negative 8/3 plus 18 minus, plugging in the 0, we just get a 0. So 18 is 54/3, so we have negative 8/3 plus 54/3. So 46/3 square units. So in our second one, our interval is now on 2, 4. But here, the place where these two meet is on our interval. In other words, we have that change in behavior like the last part of our previous example. So this time, again, we need 2 sections. Now, as to where they meet, just set them equal to each other. Let x squared minus 9 equal the other equation, 0. So x squared is 9, so x is plus or minus 3. We don't really care about the negative 3 since that's, since that is not on our interval. But the positive 3 is on our interval. That's where we have the change in behavior here at 3. So we have 2 different intervals. One that goes from 2 to 3. And our top function on that interval is the 0. Our bottom function is the curve x squared minus 9. Our next chunk of the graph goes from 3 to 4. And on that one, the curve, the x squared minus 9 is your top function. The 0 was your bottom function. So then we have negative 1/3. Jumping ahead here, my apologies. Integral from 2 to 3 of opposite of x squared plus 9 quantity times dx plus integral from 3 to 4 of x squared minus 9 quantity times dx. So now we're ready to integrate. So negative 1/3 x cubed plus 9x evaluated from x is 2 to x is 3 plus 1/3 x cubed minus 9x quantity evaluated from 3 to x is 4. All right, so I'm running a little shy on real estate here. So let's see, so plugging in R3 and make sure I'm centered okay. All right, decently. Let's see, negative 27/3 is negative 9. And 9/3 is 27, so that's worth 18. So we have 18 square units on the bottom piece of the graph. Now we look at how much is on the top piece of the graph. So 64/3. I almost forgot to do my subtraction part of the problem. My apologies. I'll scooch you over a little bit. So we plugged in the 3, now we've got to plug in the 2. So minus, plugging in the 2, we have negative 8/3 and plus 18. So there's our first subtraction problem, plus, I'm not going to fit that all on one line. Our next one, plugging in the 4, 64/3 minus 36, minus plugging in the 3, 27/3 is 9, and then minus 27. So we plug and chug all that, we should get to 64/3 square units. Okay, so then the next ones, look at what happens if we don't just have the x-axis every time. So we're going to find the area. Bounded by, you'll sometimes see this bounded abbreviated as BDD. F of x is x plus 1, and g of x is x squared plus 4. X is negative 1, and x is positive 2. So these two, x equals a constant, that's basically telling you your left and right bounds. So from negative 1 to 2, x squared plus 4, we have a parabola opening up. X plus 1, we have a y-intercept of 1 and a slope of 1. So it looks like on this one, the curve is always going to be higher than the line. We're looking from negative 1 to positive 2. So kind of an unusual shape that we're looking at, but we want to know how big that red area is. So on this one, they don't cross, so I don't have to break it into two sections. So just negative 1 to 2, we use the whole thing. And our curve was the top one. The curve then was the x squared plus 4 minus the line was our bottom function, x plus 1. Close it up, times dx. So then we turn it to the integral from negative 1 to positive 2 of x squared minus x, and we have a plus 4 minus 1, so a plus 3 times dx. So a third of x cubed minus half of x squared, so we're just integrating one piece at a time, plus 3x. Quantity evaluated from x is negative 1 to x is positive 2. So then we have 8 thirds. 2 squared is 4. Negative 1/2 times 4 is negative 2. And 3 by 2 is a plus 6. And plug in our negative 1. Negative 1/3 minus 1/2 minus 3. So then we plug and chug on that guy, and we should get, 63/6. And of course, square units. And actually, my apologies, I shouldn't leave it that way. 21/2 square units once we finish simplifying it. So it doesn't necessarily have to be a 0 minus something or a 0 plus, or something minus 0. These aren't guaranteed to be zeros. So you could have non-trivial functions. But the idea is the same, top function minus bottom function. All right, so next one, we'll take a look at BDD, remember, is bounded. Find the area bounded by f of x is x squared minus 3, and g of x is 4x plus 2. So you might look at that and think, well, wait a minute, there's something he didn't tell us here. He didn't tell us where to look. In this case, these two will meet in a way that they close off one section of the graph completely. And let me go ahead and sketch. As you've seen from my work, it doesn't have to be a beautiful work of art for the sketch to be useful to us. Vertex at 0, -3, opening up. Y-intercept at 0, 2, slope of positive 4. Obviously not exactly to scale, but this section in here is enclosed by just those two functions, the line and the curve. So sometimes they'll just leave it up to us. If they say find the area bounded by these two things, we find the enclosed area that they make, and then we have to find the two x value endpoints. How do we find them? Set them equal to each other and solve. Use a let line. Let x squared minus 3 equal 4x plus 2. So x squared minus 4x minus 5 is 0. So x minus 5 by x plus 1 is 0. So x is negative 1 or x is 5. So now we know where they meet. We know that our left bound is at x is negative 1. We know our right bound is at x is 5. So then our area integral from, now we know, negative 1 to 5. Still keeping that format of top function minus the bottom function. Top function this time was the line. Minus bottom function this time was the curve. Close it up, multiply by dx, so integral from negative 1 to 5. A little bit of cleanup here, opposite of x squared, plus 4x, and we have a plus 2 plus 3, so plus 5. Close it up times dx. So negative 1/3 x cubed plus 4 times 1/2 x squared plus 5x from x is negative 1 to x is 5. And we do a little bit of cleanup and then we'll plug and chug. So now we would have negative 1/3 x cubed. 4 times 1/2 x squared is plus 2x squared and plus 5x. And we're going from, as before, negative 1 to x is positive 5. So negative 125 thirds plus 25 by 2, 50 plus 25 minus a 1/3. So 1 negative here, 3 more there, 4 negatives. We'll kick it over to positive. Negative 1 squared is positive 1. 1 by 2 is plus 2. And 5 by negative 1 is negative 5. So we plug those guys in and we should get 36 square units. So that one did land us on a nice pretty integer. So there are 36 square units bounded by those two functions. So if they don't tell us where they meet, it's up to us to figure out where they meet. So we have you all try one of your author's ones again. So same question, find the area bounded by, and we'll just give you some new functions. So do f of x is 6 minus x squared, and the identity function, g of x is x. So go ahead and pause it, sketch it out, see what you come up with. Okay, welcome back. So your sketch, 6 minus x squared, a parabola, opening down, centered at 0, 6, and of course, the identity function. So that's the area we're looking to measure. We need to find out where exactly they meet. So we just use our let line. Let 6 minus x squared equal x. So 0 is x squared plus x minus 6. So we just set one side to 0. This one is solvable by factoring. So we have a plus 3 and a minus 2. So x is negative 3 or x is positive 2. So now we have everything we need to set up our integral. Left bound negative 3, right bound positive 2. Top function was f this time. Bottom function was g this time. So that's the integral from -3 to 2 of opposite of x squared minus x plus 6 quantity times dx. I'm going to go ahead and flip this. So -1/3 x cubed the integral of minus x would be -1/2 x squared, and the integral of 6 is plus 6x. And we're going from, as before, -3 to +2. So plugging in the 2, -8/3. 4 times -1/2 is -2 and plus 12. And plug in the -3. We have -1/3 times -27 is +9. And then we have -1/2 of 9, or -9/2, and -18. So then we, close it up there. So plugging and chugging, and we should get 125/6. All right, so that should give you enough ammo to practice with 6-1. So I would recommend 9 to 25 on the odds, and 31 to 55 also on the odds. Or if you're interested in the electronic version, let me know and I can upload a similar electronic assignment. All right, if you have questions, please get in touch. Otherwise, I'll see you next time. Stay safe out there.